Thanks for the organizers inviting me to India. This is actually my first visit to India, so I'm very happy about that. So the talk will be about the role of logic in probabilistic inference and machine learning as has been pursued by my group for a while now. So what I'll show you is a perspective that's been evolving over about 10-15 years and got accelerated over the last few years, especially the machine learning part. So the first segment is probabilistic inference, and in the last few years was machine learning. And in fact, it got to the point that there is enough substantial material on the subject that I've talked to some of you that I'm in the process of writing a second book on this subject. The first was dedicated to probabilistic reasoning. Okay, so here's the agenda. So there's two parts to this talk. The first will be focused on logic in probabilistic inference, and the second is logic in machine learning. And in the first part, what we'll do is something very specific. We'll look at 4 probabilistic queries. 3 of them are very classical. They've been around for decades, and they're the bread and butter of a lot of work in probabilistic reasoning. And the 4th is more recent. And then we're going to see how we're going to solve these queries in a systematic way by reductions to logic. And some of these actually techniques are state of the art, as you'll see. And we'll contrast that with the classical way of doing things. And then in the second part, we're going to see the machinery that we developed for this part will be used to actually now learn. And the highlight, I'll get more to the agenda later, but the highlight is we'll see how we can learn from a combination of data and knowledge. Knowledge as expressed using logic, together with data. A problem that you'll see extremely practical. All right, so let's get started. So these are the queries that we're going to be looking at in the first part. And we're going to do these queries with respect to graphical models, or what people call probabilistic graphical models, in particular Bayesian networks. But they basically apply to other probabilistic graphical models as well. So the first is what people call prior and posterior models. The other one is what people call MPE, most probable explanation. At least this is the way it appeared in Yuda Perl's book from the 80s. Now people have been referring to this as MAP. And also from Yuda's original book from the 1980s, the third query is MAP, maximum posteriori hypothesis, which people now call partial or marginal MAP. These are the new names in the NIPS and ICML literatures. And then the last query, which is the most difficult and the more recent, is something called the same decision probability. We're going to use this Bayesian network as an example to illustrate these 4 queries before we move on. But basically, what a Bayesian network and generally probabilistic graphical model is you have some kind of a graph, and Bayesian networks is directed, and then you annotate that with numbers, and that's one way of building a probabilistic model. So in this particular Bayesian network, which I put here, you have the individual gender or sex, male, female, whether they have a certain condition or not, and 2 possible tests that you can perform that will bear on this test, right? So the test results could be positive or negative, positive or negative. Now realize this test depends only on the condition, but this test depends both on the condition and the gender of the patient. So the false positive rates are specific to gender. That's why it has both of these as. So in these probabilistic models, you have this graph, which you can think of it intuitively as showing the causality of the domain. So these edges can be thought of as direct causal influences. And in this case, it really makes sense, right? So, but it actually has a particular mathematical meaning in terms of probabilistic independence. The details do not matter, except that when you draw this graph, SC, T1, T2, and put these edges, for example, you already told us that once you know the value of C, this test result becomes independent of that. Now, they are not independent a priori. If you tell me the result of one of the tests, that influences what the probability of the second test might be, but given C, they become independent. So there is a particular mathematical meaning of these graphs in terms of independence. Details do not matter. But the other thing you need to know about these probabilistic models is beyond the graphical structure which communicates independent statements, then you have to annotate them with these numbers. So for every variable, you need to give me the distribution on that variable given its parents. So this guy has one parent, and this is the table that shows for sex being male, what's the distribution on condition. So actually, there's 2 distributions here for C. One condition on S being male and the other on S being female. That's basically it. And you do the same for every node. So for this T1 result, you have to give me two distributions on the result of T1 depending on whether C is yes or no, and that's this table. So basically, you give it the distribution for a node given its parent. In this case, you have to give the distribution for this guy for every possibility of C and S. So that's 4 of them, right? So 4 distributions for this guy. That's what the Bayesian network is. And these probabilistic graphical models all look basically similar in the sense that you have this graphical structure that represents conditional independence and numbers. And the key thing about these models is the constraints of the independence constraints of the graph together with these numbers are satisfied by precisely one distribution. So when you do this, you have really specified a unique probability distribution, and that's the distribution that becomes the basis of queries. So all of the queries now we're going to ask are about that distribution. This is the first kind of query where you tell me what are the marginal distributions over the individual variables, and these are shown in these boxes. So according to this, if you just pick up an individual and run T2 on them, 15% it will come out positive, 15.3, and so on. Again, an average individual, 3.2%, they have the condition, and so on. And here's the posterior marginal. In this case, I have evidence. I have an individual, and I say that this individual tested positive on the first test, tested negative on the second, and look what happens to these probabilities. They got updated. So this was 3.2. And now 45%, 0.3. And now these are called posterior marginals because they are conditioned of this particular evidence, right? Prior and posterior marginals, typically the most common kind of queries, all right? So here's one more query. This is the MPE, or the most probable explanation, and it's an optimization query. So the idea here is, by the way, we augmented the model by another variable called agree. So the idea is I want to be able to come and tell you, look, there's an individual that took both tests. I just want to tell you that the two tests came out the same. I don't want to tell you whether they came out positive or negative, right? Just that they came out the same. You can do this by adding one auxiliary node and make this basically the table, or what we call the CPT for this node. You can imagine what it's going to look like a logical gate, right? So the probability will be 0 and 1 depending on whether this thing agrees. Now, you have 4 variables, binary, that's 16 possible combinations. And now I'm interested in the combination that's most probable, that has the largest probability. That's the MPE, and you can see it here. So according to this, the largest, or the configuration or the instantiation with the highest probability is that you have a female that doesn't have the condition and both tests came out negative. And this is showing what the probability of that is. That's 46.99. Okay, so that's called the MPE. That's called the map. Very similar to this, except that instead of optimizing over all variables, we're going to optimize over a subset of variables, and you choose that subset. So in this case, the user chose these two guys, and I want the most likely instantiation of these two variables. And in this case, it happens to be a male that has that doesn't have the condition. That's the most likely configuration of these two variables given this particular evidence. Realize that this is not the projection of MPE, right? If you take the MPE, which is the optimal over all variables, and take the subset of it, that's not the same as this guy. In general, they do not. Now, interestingly enough, the complexity of this query and the previous one are very different, as you'll see in a little bit. The last one I'm going to introduce, which happens to be most difficult computationally, is something we introduced a few years back. And it comes up in decision making. And it goes like this. Okay, so this is a different Bayesian network about farming community. You artificially inseminate a cow, and then you want to tell a few weeks later whether the procedure was successful. So you have the node that represents whether the cow is pregnant or not. This is the progesterone level, which is influenced by pregnancy, and then you have a scanning test that directly caused by pregnancy, and then you have a blood and urine test that look at the progesterone level. So basically, you're going to look at these 3 tests, and then based on that, you compute the posterior to decide whether pregnancy or not. So typically, what people do is use this as what we call a classifier, in the sense that you have evidence. Let's say I ran the scanning test and it was negative. So before it was 87%. That's the prior probability of success for these kind of procedures. But now the test is negative, then it's down to 40%. So typically you have some kind of a threshold, like let's say 90%. If the probability is above that, then you say yes, otherwise no. So you turn that number into a decision. So in this case, the decision is pregnancy no. That's how we use these typically to do classification. And then, of course, you use this basis of decision, do I repeat the procedure or not? So what is this new query? The query is, suppose you're in this situation, right? According to this, no pregnancy, correct? But realize that you have 2 more tests that you can do. So the question in decision making, it's called the stopping criteria. Do I stop here and make a decision based on the information that I have, or should I go collect more information? It's a never-ending question, because usually there's so much information you can collect and you have to stop at some point. Okay, listen to this. Here's the query, the fourth one. What is the probability that my decision of no will stick even if I go and observe these 2 guys? It's an expectation of a decision. Makes a lot of sense, right? If that probability ends up to be very high, then don't bother, just move on, right? Interesting enough, for this particular example, if you compute the SDP, it's called the same decision probability, it ends up being 78.7%. So it's almost 79% chance that this decision will stick after you observe these 2 guys. Now, depending on the application, you may decide to get more information or not. Here's another example. In this case, the scanning test came out positive, not negative. And therefore, the probability is 99.8, so the decision is yes. In this case, the SDP, and remember, when you do the SDP, you have to do it with respect to variables that you may observe. The SDP in this case is 100%. Don't bother. There's no way on earth that this probability will drop below 90% by observing these 2 guys. And you can see what's happening here. It's kind of an expectation. That is, the formula for the SDP is, look, I have 2 variables, 4 possible outcomes. Let me look at every outcome and see what happens under every one of these outcomes. What decision do I get? And then I weigh by the probability of that outcome. So it's an expectation of a decision. So this ends up being the hardest problem of all. All right, so this is relatively new, about maybe 5-6 years old, maybe a little bit more. But it's considered relatively new, and it's surprising that it was missed actually in the literature. Okay. Now, this is the complexity of these queries. MPE is, we're talking about the decision versions of these. Decision version of P is NP, marginals is PP, map is NP to the PP, and this guy is PP to the PP. Now, you will get, I'm not sure how much people are familiar with these classes, but in a little bit, we're going to talk about the prototypical problems for these classes. And you'll get more intuitions of what's going on. Okay. So the next thing I'm going to mention is, say something about how these problems are traditionally solved, because there's a long tradition for solving these problems, and point to an issue with these methods before I tell you about how we're going to solve them, because the way we've been solving them is different than tradition. So if you look in the literature on these problems, you find 2 kinds of algorithms, exact algorithms and approximate algorithms. People may have heard of something known as the joint tree, variable elimination, and conditioning. These are the 3 classical algorithms for solving these problems exactly. And then there's all kind of approximate inference techniques based on belief propagation, sampling, and so on. Now, the issue with this is the following. In this community, in the classical machine learning and probabilistic reasoning community, there is a perception on what is the divide between exact and approximate. What is the limit of exact inference that if you hit, you have to go to approximate? And I'm going to explain this to you now. And actually, one of the main things, observations of our work, is that limit is incorrect. That line that people have drew there is extremely conservative, and I'll explain in a second. But in that literature, there is this notion of tree width, which is one. How many people have heard of tree width? Just in case. Okay. Tree width is a number. I give you a graph, and you compute the tree width. It's a number. It is a measure of how close a graph is to a tree. So it's tree likeness. So if tree width is 1, you have a tree, basically. And as the number goes up, then you're further away from a tree in a subtle way. These exact algorithms all have this complexity. They are linear in the number of variables, but exponential in tree width. So if you have a probabilistic graphical model whose tree width is small, you're good. If inference is efficient. Now, if the tree width is high, though, this is where the dilemma is. The perception is that you cannot do exact inference, and that's not correct, as we will see. Now, the reason why this perception is there, because these algorithms, when they operate on a probabilistic graphical model, their behavior is insensitive to the numbers that appears in the model. So I can give you two graphical models that have the same structure. If I put numbers differently, these algorithms will still do the same amount of work. And as you'll see, actually, where you get sometimes tractability is because of the properties of the numbers or the parameters. So if you have an algorithm that cannot exploit these parameters, then the tree width barrier is correct in a sense. So again, the perception is tree width is high, you have to go to approximate inference, and actually that's not the case. And again, the trick is you want to be able to capitalize on the properties of the numbers. And I can tell you right now what these properties are. There are two kind of properties of these numbers. One of them is when you have 0, 1 parameters, and these kind of logical constraints that are encoded in the model, right? That can buy you, tractability in some cases. The other one, and that's pretty important, it's called context-specific independence. And let me explain this here. This is a fundamental notion. If you have, let's say, 2 nodes and a child, and let's call this A and B and C, think of this like an OR gate. Now, if I come and tell you A is 1, you already know that this must be 1, right? And therefore, this became independent of that guy, correct? Now, but if I tell you this is 0, this is not independent of that under 0. Under 1 it is, but not under 0. This is a notion of independence that you cannot capture in a graph because it indexes variable values. And that's what people call context-specific independence. The reason why graphical models are popular is because the graph structure encodes these independencies that these algorithms utilize to decompose problems and so on. But here's an additional type of independence that they're not actually utilizing. And the only way to utilize it is to look into the numbers and start actually exploiting them, right? It's very simple intuition, and that's what's missing in some of these algorithms. Okay, this was a chart from one of the competitions run by UAI, which basically makes this point concrete that I've just mentioned, that what you have here is these systems that are based on tree width, and you can see they die off when tree width reaches a certain number. And this is one of the systems that we have called ACE, which is based on the techniques I'm going to mention. It actually finished the whole suite. And some of these networks, on average, the tree width as we can compute it was around 50, the average, but they had some of them tree width in the hundreds. So they were all solved exactly. All right, so based on the techniques that I'm going to mention next. All right, so how are we going to solve these? Using the textbook technique of reduction. You have a class, complexity class. You have a problem in it, prototypical, that's complete for that class. So according to this paradigm, you build a solver for this guy. And then if you have another problem in the class Y, instead of building another solver for it, you go and reduce it to X. You solve X, and then you get the answer to this guy. So what we're going to do here is use this paradigm. And then you have to ask me, what are we going to reduce these problems to? OK. Here are the 4 classes, and here are the prototypical problems for these. SAT, we all know SAT. Maj-sat, I'll explain. E-maj-sat and maj-maj-sat. All of these are problems on Boolean formulas, right? The input is a Boolean formula. In some cases, a little bit more than a Boolean formula. I'll explain that. So what's going to happen is we're going to solve these problems by reducing to these problems. So I will mention two lines because there's two parts to this picture. One is reductions, and we've started this a while back, doing reductions to these problems, starting from over 15 years ago, and the latest was just last year, where you reduce these guys to these problems. Now the question is, the second part, which is maybe more interesting, is how am I going to solve these guys? Those will also be solved in a systematic way. So the other thing that we've been doing over these is one approach, one systematic approach to tackle all of these guys. And the gist of it will be that the Boolean formulas that correspond to these problems will be compiled into certain Boolean circuits. And if the compilation process succeeds in solving these problems, it can be done in linear time on the circuits. So there's two parallel pictures. Reducing these problems to these classes, reducing these probabilistic reasoning problems to these, and then solving these in a systematic way through a compilation. And that's the other part of my research program on knowledge compilation. You give me a Boolean formula, I compile it to a particular circuit with certain properties. If it has certain properties, I can do SAT in linear time. If I add one more property, I can do this in linear time, And part of what we've been doing is identifying what properties on Boolean circuits make these problems solvable in linear time and how to build compilers for enforcing these properties. And that's what I'm going to review next. And here I have to, before I embark on this, because of this picture that has been emerging over a decade now, that gave the inspiration about a year and a half ago to start an effort with a few of my colleagues that we call the Beyond NP initiative. And the idea is, because of this picture that already most people here know about SAT, that in SAT you have this prototypical problem, and people, when they want to solve NP-complete problems, they reduce to SAT, and so on. Why not do this for other complexity classes? Right? And this was the vision and motivation behind this Beyond NP initiative, which is currently a website where we actually have been collecting solvers and putting educational materials. We had an initial workshop on this, the first workshop last year. And let me just do a little bit more on this. I mean, I'm preaching here for the converted, but let me just mention one importance of this is, and this paradigm here that I'm mentioning is, this technique is independent of representation. So even though I'm going to illustrate it here for Bayesian networks, where people have been using this is with respect to new representations. Right? Bayesian networks have been around for a very long time. There is a very long tradition of algorithms, so you have options. But when you start developing new representations, the burden is on you to come up with algorithms. So if you want to invest in dedicated algorithms for those representations, that's quite an investment. So what people do now is reduce. So here's what I'm going to do next. I'm going to explain to you these guys. You know what this is, I'll explain these. And here's something that I found surprising. These, for example, I find out that even people that heavily involved in logic, and maybe in complexity, and maybe in some of these areas, are not aware of maj-maj-sat and e-maj-sat, for example, that these exist and have names, and so on. So what we're going to do is quickly review these 4 problems, and then show you how you can solve them by systematically compiling into circuits. Okay, we know SAT. I'm going to use this example, Boolean formula over ABC. Satisfiable, yes. Here's a satisfying assignment. Maj-sat is counting. Basically, same problem, except now I ask you, is the majority of instantiations satisfying? Right? So in this case, 1, 2, 3, that's not majority. The answer is no. This gives you probabilistic reasoning. Once you solve, once you can talk about majority, and there's 2 variations on this I have to mention, because typically people don't reduce to maj-sat. They reduce to 2 variants on them. I'm going to mention next. One of them is what we call model count, which is I want to count. How many? And then the answer is 3. So it's not is the majority. It's like give me the number, right? And actually the one that actually people use is not even model counting, is weighted model counting, where now I give weights to the different instantiations, and now I ask you, the added weight of satisfying assignments. So I want the number 0.14 in this case, where you add these weights, right? That's weighted model counting. That's the most common thing that people reduce to when they do probabilistic reasoning. And later I'm going to show you one reduction only, which would be to this, as a sample of what's going on, how these things work. You'd see how intuitive and simple it can be. Now you're going to tell me, wait a minute, how do you specify these, right? So the typical way this is done is you assign a weight to each literal. So x not has a weight, not x has a weight. And then the weight of a model or a variable instantiation is just the product. So the weight of A not B, C is the weight of A multiplied by the weight of not B. So you can see with a linear number of weights, you induce weights on all instantiations. And that's weighted model counting, WMC. We're good? Okay. So now we have SAT, we have maj-sat and its variance. Now we want to do e-maj-sat and maj-maj-sat. Okay. For the next two problems, now you have to split your variables into two groups to define these problems. Right? It's not just a Boolean formula. It's a Boolean formula with a split of the variables. So here's the Boolean formula. You split the variables. In this case, we're splitting them into x being the variable c and y being the variables a, b. Right? Now look at the first question. The question is there an instantiation of x under which the majority of instantiations y are satisfying? Okay, the first part is the NP. Is there an instantiation you're searching for? Just find one, we're good. Now, if you show me one instantiation, say, is this the guy you're looking for? What do you have to do? You have to solve a PP problem. Is there an instantiation of the variable x under which the majority of instantiations y are satisfying? That's why it's NP to the PP. It would be NP if PP was for free, if counting was for free. Okay, now you have to guess this one. You have to guess this one. So same split of variables. What and the complexity, maj-maj-sat comprises PP to the PP. Who wants to guess this one? You want to guess it?
No. So is there a majority of the C such that the majority of...
Yeah. Is there a majority of instantiation of X instantiation under which the majority of Y instantiation is satisfied? Counting and counting, right? And this is the expectation. This happens to be the SDP because it's like you are really looking at all possible outcomes of the things you can test, right? That you're counting those. And if you look at one and you want to say, is this the one I should count or not? You have to compute the posterior to decide what the classification is. Is the decision yes or no? So you're counting a number of things. And when I show you one, I said, should you count this or not? You have to go and do a counting problem. And that's why it is actually PP to the PP. Okay, so here's what the picture looks like now. And now what I'm going to do is I'm going to show you one reduction. So here's the thing. I'm going to just show you the reduction that's used for this, and then we go to that part about the circuits and how do we solve these problems in a systematic way. That's actually pretty interesting, as you see. And I can tell you right now, at the end when we finish the story, you'll judge. It's really appealing. And then one of the questions is, where do people with backgrounds like yourself can contribute? And I'll tell you the bottleneck is going to be in this case, which is compiling these Boolean formulas to these problems to circuits with the right properties that I'm going to mention. That's where the biggest impact can be made. And that's where the bottleneck is in terms of what we can do today or cannot do. So, but let me show you one reduction, just one, to give you an idea of how this works. And then we move on to how do we solve these problems systematically by compilations to circuit. Okay. Here's the Bayesian network. 3 variables, A, B, and C. Now, the variables are binary. So every variable has 2 states. So for this guy, I need 2 parameters, theta A and theta not A, right? Those are the 2 parameters, probability of A true, probability of a network. For this guy, how many parameters do you need? For every state of this, I need a distribution. Distribution is 2 numbers, right? 2 states, 1 distribution, another state, so 4 of them. And those would be theta C given A, C given not A, not, right? the 4 combinations. Similarly for this guy. We got it? So how many parameters? 2 plus 4 plus 4. 10. Okay. According to the semantics of Bayesian networks, which I didn't explain to you, which is how do you really induce a distribution from a graph like this? Here it is. It's pretty simple. Now, why is this the case is another story. But this Bayesian network is specifying this distribution. The probability of A, B, C being true, 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 you just multiply the corresponding parameters, 1 from each. We have 2 here, 4 here, and 4 there. Pick the guy from here that's compatible with this row. Pick the guy from here that's compatible with that row, and so on, right? So it's the expected. Theta sub A, B given A, C given A. And this is true, true, false. You end up being theta sub A, B given A, not C given A, and so on. Make sense? It's as simple as this. Right? This is the implicit distribution. And when we were asking these questions, MPE and MAP and posterior, we were obtaining answers from this guy without ever constructing it. That's the whole point. Okay, now. So if I ask you, what is the probability that A is true? You have to add up these weights. Right? Think of this as one number. And I'm adding these guys. If I add these guys, I give you the probability of that guy. Okay, you're starting to see the similarity to weighted model counting? If I tell you what's the probability of B being false, you're adding these guys, correct? Okay, we're almost there. What I'm going to give you is the vanilla flavor reduction that I proposed in 2002. That was the basis of everything else, and people have done more sophisticated things later. In the way we're going to do this, I'm going to now, even though these are meant to be real numbers, I'm going to treat them as Boolean variables. So the theory that I'm going to construct, the formula that I'm going to construct, will have the variables A, B, C that come from the Bayesian network, and has these additional variables now. All of these, I'm going to view them as Boolean variables, right? So you can rename them if you want. Instead of saying theta A, you can say P sub A. But my formula is going to be over these. And look what the trick is. There was 3 variables, and these are 10, 13. So really, there are 2 to the 13 instantiations. But I'm only interested in those guys. Where look what I'm going to do. True, 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 according to the semantics of Bayesian networks, there's 3 of these parameters that participate, and the others do not. The ones that participate, I want them to be set to true, and the ones that I don't want them, I want them set to false. So really what I want is this theory. I want a formula over these variables whose models are these 8. Out of the 2 to the 13, only 8 models, which are these guys. And you know what these guys are. For example, if you look at this, the only true variables in this are 1, 2, 3. These are the ones that if I multiply their real values, I get the weight for this guy. All of the others appear negatively. Similarly, if you look at this guy here, false, true, false, according to the table I showed you for semantics of Bayesian network, these are the only 3 parameters that if I multiply their values, I get the probability of that row. The question is, how do I write a Boolean formula that has this as its models? That turns out to be very easy. You can do this effectively in linear time by walking through the Bayesian networks, and for each node, you write out a few clauses, and you get a theory that has this. Okay, we're almost there. But you see where this is going, right? Actually, you tell me with the rest. If I give you a formula that has precisely these as its models, I want to do probabilistic reasonings through weighted model counting. What should I set the weights of the different literals? For these guys, A, B, C, they're out. The literal and its negation, I'm going to give it a weight of 1. So they wash out. For these guys, the positive literal, the weight is the probability. And the negative literal is 1. So under that, if I tell you what is the weight of this guy, you're going to tell me, okay, this is contributing a 1, 1, 1. This is contributing, let's say, 0.2, which is the value of this parameter. This is negative, so it's 1. So the only contributions come from these 3. And they are the numbers that represent those probabilities. I multiply them, I get the right probability. That's basically the weight setting mechanism. So the CNF formula looks like this, very simple. A and C if and only if this. A and not C if and only if that. It's really straightforward. You look at the instantiation of A and C and you make it equivalent to the presence of that parameter. That's pretty efficient. You just walk through the network and write these guys, and this formula has exactly those models. You augment this with the weights, as I told you, and you get what you want. So let's look at it concretely. This is the row, true, true, false, and according to the Bayesian network, that's the probability. If you look at this formula and you look at this model, what is the weight of this model? This is 1, 1, 1. This is 0.3, 0.6. Everyone, and you just multiply these, you get this guy. You're in business. That's it. All right? There are more sophisticated encodings. Especially, you can use this to encode, as I said, local context-specific independence and zero parameters, but they just modify the formula. These are actually explained in my book on Bayesian networks. Okay, so now we're going to see how we can solve these problems systematically. So this portion that I'm going to mention comes from an area of AI that's known as knowledge compilation that I have been active in. And the idea is pretty simple. The idea is you have a Boolean formula. You want to ask a question about it, whether it's SAT or count how many models it has or some of these things that I've mentioned. So you can build a dedicated algorithm. Or the other approach is you compile this into some circuit structure, Boolean circuit structure, like in Boolean circuits, that if it has the right properties, then you can start answering questions by operating on the circuit. And the goal is answering questions on the circuit should be efficient. Efficient means polynomial, but actually almost everything I'm going to mention is going to be linear. So the bottleneck now is here. The hard computational algorithmic work is in the compilation. And if you compile, then, okay. Over the years, we have actually found that you can actually do a lot by only working with what we call NNF circuits, where the gates are only ands and ors. That's it. And the inputs are either variables or they're negations. So negation normal form, because negations can only appear in the inputs. And what you can do is, so these are not interesting. Negation normal form circuits don't give you much. But if you add some properties, if you insist the negation normal form has this property X, then certain thing that is usually hard becomes easy. And it turns out that there is a successive set of properties that gives you these. And that's what we're going to walk into right now. Here's the negation normal form circuit. Ors, ands, inputs, either variables or the negation. By the way, this circuit is a compilation of these Boolean constraints, which they'll come handy later. I'm going to use them as an example when we do machine learning. By the way, this is a circuit. It looks like a tree, but because we didn't share the variables. So if you see P, for example, appears in multiple places. If you were to do this properly, it would look like a circuit, but it would look too connected. So, okay. Now, here's the first property, called decomposability. This is pretty old. If you have decomposability, SAT becomes linear. You can do SAT in linear time. So what is decomposability? It's pretty simple. For every AND gate, if you look at the sub-circuits feeding into that, their variables cannot overlap. So if you look here, the variables are L and K, and the variables here are P and A. They do not overlap. This must be true for every AND gate in the circuit. If this is true for every AND gate, the circuit is called a decomposable negation normal form, or DNNF, and then SAT on this guy is actually linear time. That's basically it. Okay, now this gives us SAT. So now we hit the first layer. Now we want to go, so NP. Now we're going to go to PP. We want to count. You put one more property on this circuit, and now you can count the satisfying assignments in linear time. Okay, what is that property? If decomposability was a property on AND gates, the next property is going to be on OR gates. And it is called, at least I call it determinism. And it goes like this. For any input that you apply to the circuit, in this case, the input is all high. For any input you apply to the circuit, an OR gate cannot have more than one high input. So if you look at this guy, two low, one high. This guy, both low. This guy, one high, one low, and so on. No OR gate can ever have more than one high input at any time for any. Okay? Now, if you have decomposability and determinism, maj-sat and model counting and weighted model counting all linear time. You want to guess how the algorithm works? For just unweighted model counting. If I want to count the models of this guy, here it is. I want to count the models of the circuit. How many satisfying assignments? You want to guess how this works? It's a single pass, bottom up. Okay, usually the boundary conditions are the hardest one. Forget about the boundary conditions. Tell me what's going to happen at AND gates and what's going to happen at OR gates. Multiply at AND gates and add at OR gates. And you put ones for all literals, positive or negative. So here's the boundary case, 1, 1. Of course, this is a false, 0, okay? And then you just multiply and add. This guy has 9 satisfying assignments. So now, can you imagine now what we just did? You take a Bayesian network. You spit out a Boolean formula. You are able to compile that Boolean formula to a circuit that has decomposability and determinism, now probabilistic inference linear time by doing passes over circuits. It's fantastic. I can give you real time guarantees now on probabilistic inference. And later I'm going to give you a pointer to one of our compilers, C2D, which takes Boolean formulas, CNFs, and compile them into circuits that have these properties. One of its main uses is probabilistic reasoning, and as I just described. And the ACE system that I told you encloses that compiler. It actually does the reduction for you. ACE system takes the Bayesian network. There's multiple reductions you can use. It will apply one of them, invokes C2D, gets one of these circuits, and says, that's it. This is how you do probabilistic inference. Okay, so I'm almost done with this part. Let me just mention, because also at dinner yesterday it came out, that one of the main applications of these circuits also, aside from probabilistic reasoning, is in configuration. In fact, these particular ones, the decomposable and deterministic, were recently adopted by Toyota for its online configurator system. There was a news release from UCLA about this. The idea was they used to do configuration on servers, and now what they do is they compile manufacturing constraints and inventory into circuits, and they load them into your web browser. So if you're doing a car configuration online, the reasoning is happening inside your web browser, because it's just a circuit and doing passes over that circuit. Renault in France also uses other variants of knowledge compilation circuits for that goal. Now, let me mention 2 more things, and then we'll end this. Now, I have to a little bit not go into much details, but I want to give you a hint of what gets you to the PP to the PP. So the other development in this area is this notion of structured decomposability, where you have the circuit that's decomposable, but the decomposition is happening according to some kind of a tree structure that we call a V tree, variable tree. So the variable tree is a binary tree like this, where these guys are the variables. You can have any one of them. But the point is, the circuits, when in its decomposability, has to adhere to a particular tree structure. So this is a more restricted version of decomposability. So how does it adhere? In the sense that if you look here, AND gate must map to a node there, so that these guys are L and K, and these guys are E and A. So if you look at this AND gate here, it maps to that, L and K. Right? So it's not arbitrary decomposability. It's a structured version of decomposability that is conforming to some V3 structure. And if you have decomposable negation form that is structured, then more operations become tractable. For example, multiplying 2 of these can now be done polynomial time, which it couldn't be done if you just have normal decomposability. And the final thing I'm going to mention is moving this circuit structure is, this is the latest type of circuits, latest as of 5 years ago. And because these are the ones we're going to use in the last part on machine learning. They're called SDD circuits. They are decomposable and deterministic, but in a specific way. They are decomposable but structured, and their notion of determinism is also more specific. So if you think about it, what we have now is decomposability and determinism, and then we have a more specific version of decomposability, and what I'm going to show you now is a more specific version of determinism. And then we finish this part here. If you look at these circuits, this is not an arbitrary example, but there is a recurrent structure. Look what's going on here. OR, and there's all of these ANDs. The ANDs, just two inputs. The OR could have any number. And this recurs. The structure recurs. Moreover, if you look here, you find that precisely one of these guys is high. This is high, these two are low. This is true for every input you apply to the circuit. Anytime you apply any input vector, you're going to find precisely one of these wires is high and the other two are low. What does that mean? This fragment is acting as a selector. What's happening here is the output here is just selecting this guy where this is high. So this gives you that at most one of these guys will be high. If you have one of these circuits and you have an appropriate V3, you can do maj-maj-sat on these guys in linear time as well. This is very recent, last year. And just to give you the intuition, if you look at these V3s, you have to have V3s. Remember in maj-maj-sat and e-maj-sat, you have X and Y variables. You have to have these V3s so that the X and Y variables are located in a certain way in relation to each other in the V3. That's the condition. So if you tell me I'm doing e-maj-sat or maj-maj-sat, and here's my X, here's my Y, I tell you must use one of these V3s. And if you build one of these circuits with respect to that V3, then you can actually do maj-maj-sat in linear time. Right? So as you can see, the whole game is that of getting these circuits with the right properties. We have an SDD compiler, by the way, that does that. It's already out in binary, and we're going to release the source code soon. It allows you to compile these circuits with these V3s and all of that. Think of it more like the CUD library for OBDDs. It's kind of a similar kind of structure. Right, we have about 4 compilers out of my group. At the very end, I will give you a list of the names. They're all online. Yes?
So you have time?
To answer questions? Yes, go ahead.
So the last slide. So I got all the other refinements of the
Decomposable and deterministic.
Decomposable graphs, but except the last one, which was the selector criteria.
Right. Think about it this way. This is OBDDs, right? This decision node X. X true go this way. X false go that way. This selector thing is a more general decision node. Alpha 1 go this way, alpha 2 go this way, alpha 3 go that way. And the alphas are mutually exclusive and exhaustive.
And
that's this guy. That's this guy.
Okay.
So in fact, if you notate these differently, you get these are decision diagrams in which you're branching on formulas, arbitrary formulas instead of variables. And that actually gives you exponential separation. Okay, here we are. We finished the first part. Let me see, how am I doing on time? Okay. I'm behind. I'll have to rush through the last part. Okay, let's move on. So here's the bottom line on machine learning. Folks, look what's going on. And as I said, I'm going to just try to stay away from detail and give you the gist of it, because really in terms of techniques, what you need is very little beyond what I just said. This is a circuit, right? We know what this is. I already counted the models of this, and I said that there were 9. Here's the table. There are 4 variables, so there are 16, and these are the exact 9 that this guy says 1 on, right? Here's what we want to do now. I want to put a distribution over these 9 guys, probability distribution. Over these specific 9, not the others. And it turns out to be, so this is an observation, and then I'll tell you how we're going to use it. It turns out to be, it's easy by simply doing the following. By putting local distributions on OR gates. Here's the OR gate. 0.1, 0.3, 0.6 normalized. You have to put also one here and so on. If you do that, that induces a distribution over these guys. I'm not telling you how. We're going to skip that part. But the semantics are very simple. That's called a probabilistic SDD circuit or a PSDD, right? It has a compositional semantics. Every OR node, you can think of it as a PSDD that represents on distribution, and they cannot, this is the big guy. The whole thing is this distribution, right? It's complete and canonical. It's tractable for MP and marginals. You can do marginal queries and MPE, the first two, in linear time on this. And here's how we're going to use it. Okay, let me show you this problem. This is a challenge I usually give to the machine learning community. Look what you can do now. Classical machine learning problem. You have a department that offers 4 courses: logic, KR, probability, AI. You have data. This is what people call data. Every row tells you there are 6 students that did this, just took probability, didn't take the other guys. 17 students took logic and KR, but not probability and AI, and so on, right? So the classical problem is, learn a model from this data that I can use to reason about what students tend to do. So for example, I want to tell you, okay, here's a student who did this. What's the probability that they will do that? It's a classical problem. Now, except that, in addition to this data, we now have additional knowledge. In this particular case, we have prerequisites and requirements. Every student must take at least probability or logic. Probability is a prerequisite for AI, and the prerequisite for KR is either AI or logic. Now, the task is, I want to learn from this together with that. How do you do that? I have 2 inputs. Can you imagine how often this will come up? Now, what does it mean mathematically? Mathematically it means this. This is the original probability space with 4 variables, correct? When you learn from data, you're learning distribution over that. I'm coming to you up front. I tell you, I know that a lot of these things have 0 probability. This is your space, not that. I want you to learn a distribution over this. And I specified this how? Using the knowledge, logical constraints, and then I give you the data, right? So the way you do it here, or we've been doing it, is you take the Boolean constraints, you build an SDD circuit, you get this, you've seen it before. Here's the data. Now, you can learn the distribution by parameterizing these OR gates. The question is, what parameters do you use? The classical technique or objective measure in machine learning is you come up with maximum likelihood parameters. What does that mean? You know, Nikolai says, I'm going to put these numbers here. Then he introduces a distribution. And Supratik comes and says, no, that's not the distribution. I'm going to put another one. And then you get a different distribution. Which one do we choose? We see which one maximizes the probability of the data. That is, we look at both distribution and ask the first one, what is the probability of seeing that many, So this is the maximum likelihood principle. Well, guess what? Because of the properties that the circuit has, you can compute maximum likelihood parameters from this data in closed form, in this case. So if you succeed in compiling the Boolean constraints and you get the circuit, you get the parameters of this from that data. Now, that detail is not here, but that's part of the literature on this subject. So you can take knowledge, compile it into a circuit with the right properties, and then you induce a probabilistic model by parameterizing the OR gates from data, and now you have this guy, you can use it. This is your new probabilistic model, the PSDD. Now, what I'm going to do next is, again, even pull up one level up to tell you what you can do with this. So this is not it. This is the beginning. Let me tell you what you can do with this. We know what combinatorial objects are, right? You can use this box, the box that takes a Boolean formula or a set of logical constraints and data, to now, in a systematic way, start learning distributions over combinatorial objects. Let me show you how. And one of these applications now is big for us. We already have 3 papers on this. One was just presented at NIPS this week, and one will be presented at AAAI. on learning route distribution. So let me show you this. This is really fun. Okay, grid, source, destination. Here's a route. One way to go from this to that. There may be other ways to go from this to that. The data I'm going to give you is different ways people went from A to B. And I want you to learn a distribution over the possible routes so that you can use it to reason about what people tend to do. I want to tell you someone is going from this to that and he already did this. What's the most likely completion of the route? Right? Okay, how do you do this? Normally, you're on your own. You have to find a dedicated way of doing it. Let me show you this and another example which will give you the gist of how you can do this systematically. Okay, every edge on the grid is a Boolean variable, right? 24 Boolean variables. The idea is what? A route is a variable assignment. These variables are high, all of the others are low. We're good so far? Okay. Except, here's a variable assignment. That's not a route. You're with me? So, routes are a subset of the variable assignments, correct? How do you capture these? SDD circuit. You can write a Boolean formula whose satisfying assignments are precisely the valid routes. If you compile these into an SDD circuit, you're a business. Now you can learn distributions over routes. And this is not a theoretical exercise. We started with this as a theoretical exercise in 2016. We just scaled this to a real map. This was what is presented yesterday, actually, at NIPS. My students were there. We took an actual map, but we had to do hierarchical maps. We couldn't scale to a real map. We had to partition it and introduce the idea of a hierarchical map. The idea is, if you're going from Venice to Westwood, that's my neighborhood in LA, you decide to go from Venice to Santa Monica and then to Westwood. You plan at that level. And then you start doing the intermediate things. Or if you're going from one state to the other, you plan of going through a certain highway. But once you decide that, what you do on this state is independent of what you do in that state. Doing that, we introduce this notion of a hierarchical map, and then we have a more sophisticated approach for doing this. But I want to give you one more example of this game. You know what total orderings are, right? Permutations. This is another example application in machine learning where people want to learn user preferences. So the idea is, in this case, a user preference is just a total ordering on items. It's sushi, right? There's 10 items. Here's one user saying, I like this first, this second, this third, da. Here's another user says, no, I like this first, this second, this. Okay, so we have n items. The probability space is n factorial. I want to induce a distribution over that from data. What is the data? The data, I go to all of you and I say, each one of you give me your total ordering or a population. I want to learn from that. How do you do that? You either have a dedicated approach for this, and people have been investigating this for decades. There are tons of ways of doing distributions over total orderings. Or if you want to do it this way, look what you do. I have n items, n positions. I put n square variables. What does that variable mean? Well, let's pick this guy. That this variable, if it's high, it means item 2 is in position 3. Right? Same story. These guys are high, all of the others are low. That's a variable assignment that does correspond to a valid total ordering. Item 2 is in position 1. Item 4 is in position 2. Item 1 in position 3. And item 3 in position 4. That's good. This is not good. Right? That's a truth assignment that does not correspond to a valid total ordering. Item 1 is not placed anywhere. Item 2 is placed in 2 positions at the same time. That's bad. What do? You write Boolean constraints. In this case, you can write 2 n constraints. One of them says every item is in exactly one position. The other, every position hosts exactly one item. And then you can filter out the bad guys and keep the good ones. You do that using an SDD circuit, you're a business. Now, guess what? This thing that I just described, in an experimental study which we reported 2015, beat a box based on the Mallows model. The Mallows model is one of these detailed or dedicated distributions for total orderings. That's been around for a long time. It's not even tractable. And we actually had to use what people call their mixtures of, because the mallows is unimodal, so it's not competitive. We had to mix 20 mallows models to start getting it to produce comparable results to what I just showed you. What I just showed you had no notion of total ordering except the Boolean constraints. And it was actually, what this basically shows you is the quality of the learned models. Eventually they were similar. This is the PSDD which I described, and this is the other guy where we were increasing the number of mixed distributions, 20 of them, eventually to get comparable results. So it's pretty impressive that you can get something that is so general, that is not specific, to be that competitive with a dedicated model to ranking. Okay, I wanted to just say one last thing, but I will say it actually. Everybody went overtime, so I will do 5-minute overtime. Is that okay, Sorti? This is the last thing I want to say here, is because this is interesting. In machine learning, people talk about two types of data. They talk about complete data, like this, where you have the variables, and every row, I know the value of every variable, right? So it's a patient. They had this, they did this test, they did this, then that means I know everything about the patient. Now, this is unrealistic, right? Typically, you have incomplete data where you say, for this patient, I know this and that, but I don't know that, right? Complete, incomplete. It makes a big difference in the properties of learning algorithms, whether how they converge, the complexity, whether it's complete or not complete. You can imagine this is easier, this is hard. But listen, for logicians, what's the difference between these two guys? Logically, this is what we call a full variable instantiation. This is what we call a term, partial variable instantiation. So in one case, I'm telling you, I know the model. I know the full variable instantiation. Then I know it partially by specifying some of the value. Why do I have to restrict ourselves to this? Why can't I write a Boolean expression like this? What prohibits me from doing this? Nothing. Now, these kind of databases or data sets are not part of the literature. Let me show you a concrete example of where this come up. Look at the total ordering business. This is what a complete data set looks like. I go to each one of you, I tell you, I want a total ordering. Tell me for every variable, what's in position 1, what's in position 2, what's in position 3. That's total ordering. Okay. In an incomplete data set, I'm telling you, fine, number 1, number 2, you can keep some of them empty. Don't tell me, you may not know what is your third, right? It's better than that. But what I just described, you can do this. You can tell me anything about your preferences. Right? Very practical. Now, why is this stuff does not exist in the machine learning literature? It's very simple. This is my explanation. If you look at the algorithms for learning from data, the classical one, for example, for learning from complete data is known as EM. The way they work is like this. They start going through the data set, they pick the examples one by one, and they condition. So they have some kind of distribution. And then they condition the distribution on that thing. Conditioning on a variable assignment, whether full or partial, is bread and butter for algorithms in machine learning and probabilistic reasoning. Conditioning on arbitrary Boolean expression is not part of the repertoire of these methods. If you want to do this and do it well, you need to manipulate logical statements and know how to play this game. There are ways to force it to become the other, but it's not as effective. In the framework that I gave you, if you can take an example, which is a Boolean formula, and compile it into a circuit using the same V-tree, you can do this in polynomial time. Right, so this is another example where, logical manipulations matter. Okay, I'm going to skip. Oh, well, maybe this is useful. This, just to give you a sense, this is from the domain of partial ranking, not total ordering, where you have tiers. You do user preferences, and you say I have only 4 or 5 tiers. That's 1 star, 2 star, 3 stars, and so on. You can get a sense of the size of the circuits. This is from 2 years ago, right? So, but you have to remember that this is very easy. Doing a pass on this is in no time, right? A 1,000,000 node circuit is not scary. And I'll skip the rest. So here we are. This is the conclusion. This is our webpage, Automated Reasoning Group. You're going to find a publication tab where a lot of these publications that I pointed to, software tab. This is the SAM-IM system. There are particularly compilers. C2D compiler compiles into deterministic circuits. That's binary, not open source. Mini C2D is a version of this which is both open source and has a modular design. I talked to some of you yesterday. If you want to change something, this would be how you'd go. SDD library, I already mentioned. ACE is a system that takes Bayesian networks and reduce them to Boolean formulas, invokes C2D to compile them into circuits and give you back the circuits to do reasoning. All of these are available. Let me also just mention one more thing. This second part that I went over quickly for machine learning, there is a 40-minute on that online. I gave this talk at the Simons Institute last spring. So if you want to look at the machine learning part simplified into 40 minutes, which I did in 15 minutes, it's this talk. I also have some views on what's going on in AI, the current state of AI. And there is a position paper on this available on the archive, which is linked by this YouTube video. You may find that interesting if you want to know what I think about what's going on. Thank you very much.